Good afternoon. It is a pleasure for me to introduce today for the IPARCOS colloquium Stefania de Curtis, who is a research director in theoretical physics at the NFN section in Florence. After graduating in physics at the University of Florence in '83, she got the PhD at CISA in Trieste in elementary particle physics. And she was guest of Raoul Gatto and collaborators at the physics department of the University of Geneva. First, she obtained a Fondazione della Rizia grant, and after that, she had the support of the Swiss National Science Foundation. In 1988, she got a researcher position at the NFN Florence section, where she continued to spend several periods also at the University of Geneva and at CERN, where she has been carrying out research in the field of physics of fundamental interactions, which is what she's going to talk about today. She has been coordinator of the theoretical group of the Florence section since 2005. She regularly teaches and is a member of the board of doctorate in physics and astrophysics of the University of Florence. And she has been a contributor, well, actually one of the founders of the Galileo Galilei Institute for Theoretical Physics, GGI, and its transformation into the National Center for Advanced Studies. And this is the institute that she's now the research director, and it's located in Florence in the Acetri Hills, close to the place where Galileo developed most of his work. Since 2013, she's been coordinating the PhD schools at this institute at GGI, and is part of the organizing committee of GGI lectures of the theory of fundamental interactions. Since 2017, she's a member of the plenary European Committee for Future Accelerators, ECFA. It's now discussing what will be the next steps in the European policy for particle physics. And in December 2019, she was nominated the director of the GGI. And now we've invited her to be part of our scientific committee of the IPARCOS Institute. She is also in the INFN executive board. And she's the author of more than 100 papers published in international and very prestigious journals, very well known internationally, as well as about 60 contributions to conferences and workshops. So it is my pleasure to invite Stefania, and please, she's going to be talking today about whether the Higgs is the last, the Higgs boson particle and its discovery is the last missing piece of the puzzle, or there is something else. So thank you very much, Stefania. If you can now, please start, and thank you very much for coming and giving us this conference. Thank you.
Thank you, Jose Ramon. Thank you very much, both for inviting me to give this talk, and also to ask me to be a member of the advisory committee for the IPARCOS, the new institute that I hope to contribute to the success of this new institute. And I will bring with me the experience that I gain for the activities of the Galileo Galilei Institute that Jose Ramon mentioned in the introduction. And I just want to start by presenting this institute and his activity, just to show you what I'm doing all the days in my last period. The GGI, Galileo Galilei Institute in Florence, is a research hub devoted to theoretical physics. So in a sense, it's less ambitious than the IPARCOS Institute, which is devoted to several branches of physics and not only theoretical physics. The GGI is dedicated to organizing and hosting long-term programs and PhD schools to foster breakthroughs in fundamental understanding of the universe. And the spirit of the GGI is to favor discussions and stimulate collaborations thanks to its environment and facilities. Before the pandemic, more than 800 scientists were hosted at the GGI every year thus confirming its status as a reference point in high-level training and research for the international scientific community. And as José Ramón told, in 2018, the GGI became National Center for Advanced Studies of the INFM. Workshop proposals are selected every year by the GGI Scientific Committee, but the GGI also hosts short-term events like conferences, meetings, and schools proposed by the international scientific community and selected by the GGI Council. The last thing that I want to mention is the Galileo Galilei Medal Award, which was established in 2019, and it is assigned every 2 years to one or more scientists who have achieved outstanding results in theoretical physics. The first recipient was Juan Martin Maldacena, while in the 2021, the Galileo Galilei Medal went to 3 great scientists, Alessandra Bonanno, Thibault Damour, and Franz Pretorius, for the fundamental understanding of sources of gravitational radiation. We hope to have the ceremony for the award next October in presence, so finger crossed for that. This is just an introduction, and but let's go for physics. Let's go to my talk. As José Ramón said, the title is it's a question, actually. The particle content that the standard model is on which the standard model is based, namely the leptons, the quarks, and the mediators of the electromagnetic weak and strong interactions, seem to close with the discovery of the last particle, maybe the last part of the puzzle, which is the Higgs. But there are still several open questions. So the question is if it is really the last piece of the puzzle, or it is a portal to a hidden world. The standard model is the theory that till now describes all the phenomena in nature except for gravity. And as I say to my students at the beginning of the course, it is an extremely elegant theory. It is written just in these few lines, which on the basis of the underlying symmetry can encode the interactions between the elementary constituents of matter and the force mediators, the fundamental force mediators, the photon, the gauge bosons for the weak interactions, and the gluons. It describes 3 families of leptons and quarks. These 3 families are all equal except for the mass. The mass is increasing, going from the first to the 3rd family. And this is a crucial aspect, namely the dynamic which give mass to matter constituents, quark leptons, and the force mediators. So the question is, which is the origin of the masses? The origin of the masses within the standard model is described by a mechanism, which is the Higgs mechanism, which was introduced by Brout, Englert, and Higgs in 1964. This mechanism required the presence of a scalar field, phi, with a particular potential, which can trigger the spontaneous breaking of the electroweak symmetry. Without this field, all the constituents of matter are massless, and it is just because this Higgs field is coupled to the matter fields, and because of its constant value after the spontaneous symmetry breaking, that particles acquire masses. The Higgs field permeates all the space with a constant value, and its interactions creates something like a friction corresponding to a mass. A pictorial way to explain this mechanism that I like to show is the one which uses these pictures by Miller. Without the Higgs, as I said, all particles are massless. So you can imagine the Higgs field, which covers all the space, as people invited to a party. They fill all the space of the room, and as soon as a very important person enters the party, she interacts with people. The bigger is the importance of this person, the larger are the interactions, and the harder is to move on. In this way, the Higgs field creates a friction, and if you want, the importance of this person is equivalent to the mass that she is gaining through the interactions with the Higgs. After the proposal of the Higgs mechanism in the 1964, there was a very big hunting for the Higgs particle, in particular at the Large Hadron Collider, which is the biggest collider in the world, and it is at CERN in Geneva. The ring is 27 kilometers long, and the proton beams running in opposite directions collide in 4 points of the ring, corresponding to the 4 experiments at CERN: CMS, ATLAS, LHCb, and ALICE. There was really a strong effort for searching this missing piece of the standard model, and it was in 2012 that some Higgs candidates started to show up. These are 2 events. The one recorded on May 13, and it corresponds to a possible Higgs candidate decaying into photons. And the one in the bottom of the picture is a Higgs candidate which decays in 2 Z bosons, which in turn decays in 4 leptons. So after accumulating several of these events, finally on July 4th in 2012, the ATLAS and CMS collaborations finally announced the discovery of the Higgs boson, and it was 48 years after its theoretical predictions in, as I told you, in 1964. The mass of this particle was extracted by, if you want this plot, by the invariant mass of the 2 photons, which are the product of the decay of the Higgs, and it was estimated to be around 125 GeV. The same value is compatible with the reconstruction coming from the other channel, that is H into Z. Notice, I want to show you that now, after the doubling of the center of mass energy of the 2 proton colliding, and it is 13 TeV now, and it was 7 and 8 TeV at that time, the mass values is confirmed, and the error in its determination is, of course, lower. So we have the Higgs, and Mr. Engler and Mr. Higgs got the Nobel Prize in Physics in 2013 for the theoretical discovery of a mechanism that contributes to our understanding of the origin of mass of subatomic particles, and which recently was confirmed through the discovery of the predicted fundamental particle. So everyone was happy, and that was apparently the end of the hunting for the Higgs. But as I told you, there are some theoreticians, almost all, they are not completely happy, because there are still several fundamental questions which are not answered within the standard model. Here I wrote only some of them. The first two are within the standard model theory. Why the three quark and lepton families have so different masses? This is the so-called mass hierarchy problem. In the standard model, the masses of quarks and leptons are free parameters. They are not, they do not come from the dynamics. So the question is why nature choose to have so different values of masses for these fundamental constituents of the matter. And also, why the Higgs boson mass is so small? This is the so-called naturalness problem, and I will talk about it in a while. In fact, the boson mass, being the Higgs scalar elementary particle, is not protected by a symmetry, and so also for this value, we don't have a prediction for the small value of the Higgs mass itself. Outside the standard model, we have also other questions that are not answered within this theory. Why there is only matter in the universe and not antimatter? Why the gravitational force is so much weaker than with respect to the others? And finally, what is dark matter? And what is that energy? And the standard model is a framework in which these questions are not answered. For this reason, one is not fully happy, as I told you, and would like to find a way to embed, if you want, the standard model theory in a more general theory which can answer to one or more or all these open questions. Concerning the mass hierarchies that I mentioned before, as I show you in my first slide, the masses of the elementary particles cover several orders of magnitude, apparently without any order. Furthermore, the neutrino masses, which are not even described by the standard model, within the standard model, the neutrino are massless, and we know experimentally that it is not true. They are, anyway, 10 to the 15 order of magnitude less than the quark top mass. So one is obviously wants to find a rule for this hierarchy. And to find if there is a criterion or a fundamental dynamics which can explain the mass hierarchies. Another question is if the zoo of the elementary particles is really complete, or, as I told you, the standard model is a partial description of the nature and a part of a more general theory which will manifest energies higher than the ones explored till now. Many extensions of the standard model foresee new elementary particles. The famous supersymmetry, this is well known, associated to every standard model particle a partner with higher mass. So maybe the zoo of elementary particles is not complete. As I told you, the puzzle seems to be complete with the Higgs, but maybe the Higgs is something much more complex and is just the beginning of a new story. Just to summarize the question marks that I just was saying before, we found the Higgs boson. So we are asking, is it really the standard model Higgs? Is it the small mass of the Higgs natural? As I told you, a an elementary scalar receives radiative corrections, which naturally goes to the scale of the theory. So it is not natural to accept a so huge hierarchy between the electroweak scale and the Planck scale without a theory which can explain it. So the Higgs is really elementary, or there is a dynamic inside, is a composite particle. Is it unique, or maybe it is only the lower mass component of a more complicated multiplet? Is it the first supersymmetric particle ever observed? Who knows? And also, is it the Higgs the only responsible for the masses of all elementary particles? We saw that the big hierarchy is not explained very well by assuming that it is only the Higgs mechanism responsible for mass generation. We have to accept a huge difference of masses. So what I'm thinking is that the Higgs actually is not the end of the story, but it is the portal to a hidden world. And this motivates the search for beyond standard model theories. It is not an easy task now, because before LHC, we discovered the W and Z bosons, the mediators of the weak force. We discovered the top, the heaviest quark. So the Higgs was missing, and LHC was searching for the Higgs and eventually new particles. Actually, LHC has not shown any evidence for new particles and or interactions. So after the Higgs discovery, particle physics is no more a check of the standard model, but rather an exploration of the unknown. We don't have now an indication, a clear way to follow. This stimulated a change of attitude in particle theory community, and we started to explore alternative paradigms, and a very rich variety of models and of schemes appear on the market. This is beyond standard model theory after LHC round 2. You see that there are a lot of streets and bridges that you can follow. Naturalness or modified naturalness or unnaturalness are all of them taken into consideration. In my opinion, naturalness is still an important question to answer. In particular, I'd like to answer the question, can the value of the Higgs mass be explained by an ultraviolet theory? And if I use naturalness as a guideline, then inside of this variety of schemes, compositeness of the Higgs is one possibility, and I will show you some scenarios in which the Higgs is composite and can ask this question. That means can solve the problem of the smallness of the Higgs mass. In these schemes, since the Higgs is a composite particle, the strong force which binds the Higgs also bind other particles, other extra particles. So one have to include the fermionic partners and massive vectors as bound states of the strong force. And also one can consider extended Higgs sectors in which the Higgs is not the only one particle triggering the spontaneous symmetry breaking. And also recently, another exciting exciting property of these models has been studied. In particular, the fact that composite dynamics is also responsible in the early universe to trigger an electroweak phase transition, which is strongly first order, and so can also create the conditions for baryogenesis. And also even more exciting, it can trigger also the production of gravitational waves due to the fact that this phase transition is first order and very strong. And I will tell something about this in the rest of my talk. So, naturalness is a very deep question, and in my opinion, still a good guideline for new physics. And as I told you, the problems comes from the fact that the Higgs, the elementary Higgs of the Standard Model, is not, the mass of this particle is not protected by a symmetry, and so it naturally receives radiative corrections which are of the order of the scale of the validity of the theory. Of course, this is not a problem because the Standard Model is a theory which is renormalizable, so it is not an inconsistency. Maybe nature chose it to have a Higgs which is light, just to say, but I don't feel comfortable thinking about the fact that one need very fine cancellations in order to predict the value of the Higgs mass which was observed experimentally. In order to solve this problem, let me call it problem, new paradigms has been proposed. One is supersymmetry, and the other one, which I will follow in this talk, is strong dynamics near the TeV scale. In particular, the property that the Higgs is a composite state with the property of to be a pseudo-Nambu Boston boson. Actually, this is not a new idea. It dates back to the 80s, and the fact that the Higgs is a Goldstone boson exactly as the pion is a Goldstone boson associated to the chiral symmetry of QCD. In fact, the pion is the lowest hadron, the hadron with the lowest mass. And this is because its mass is protected by the global QCD chiral symmetry. If we take this scheme and you scale this scheme to the higher energy, you can think about the Higgs as a kind of pion from a new strong sector. Equivalently, you expect new resonances like the raw resonances in QCD here in the TeV region. Okay, so the scheme is exactly borrowed from QCD. If the Higgs is a Goldstone boson, obviously he's massless, but exactly as it happens for the pions, the chiral symmetry is not an exact symmetry, it's explicitly broken by the quark masses, and the pion has a tiny mass. The same can happen for the Higgs. That means that the global symmetry group is not an exact global symmetry, it's an approximate symmetry broken by the Standard Model loop effects. And the potential is generated, and the Higgs acquire mass at loop level. So the hierarchy problem is solved by the fact that the Higgs mass is generated at loop level and regulated by the weak Standard Model coupling constant. So, which are the basic rules for explicit composite pseudo-Nambu-Goldstone boson models? One has to start with a global symmetry above the compositeness scale, which is typically in the TB region, which is spontaneously broken down to a subgroup H. The structure of the Higgs sector is determined by the coset G sub H, and H should contain the SO2 custodial group, because we know that in the standard model the custodial group is almost exact. The number of Nambu-Goldstone bosons must be larger than 4, because 4 is the number of components of the standard model Higgs. And the symmetry G must be explicitly broken to generate the mass for the otherwise massless Nambu-Goldstone bosons. A minimal model, first minimal model, which was formulated along these lines, was formulated in 5 dimensions actually, and it was realized in a warped metric, and the Higgs in this model is the 5th component of a 5-dimensional gauge field. The symmetry is broken by boundary conditions, and that give rise to an infinite tower of resonances, the famous Kaluza-Klein modes. And the compositeness degree of the ordinary matter correspond to the localization toward the infrared brane, as is sketched in this figure. Through the ADS-CFT correspondence, we know that 5-dimensional models are dual to 4-dimensional strongly coupled theories. So, also due to the fact that composite physics is largely independent on the 5-dimensional bulk, one can just rely on the lowest modes, which are relevant for this description, and go for an effective 4-dimensional description with only one level of resonances. And these are the so-called deconstructed model from a 5-dimensional scenario. So the basic ingredients are simple: a strong sector with the composite resonances, the elementary sector with the standard model ones, and a mixing between the 2 sectors. And this is what we did for the construction of our 4-dimensional composite Higgs model, which is nothing but a 4-dimensional realization of the minimal model that I described to you. And it is based on 2 sigma model fields which triggers the spontaneous symmetry breaking. The low energy Lagrangian is then, we add to this Lagrangian new spin-1 resonances and extra composite fermions, and the spectrum is given by the composite fields which are there, the spin-1 and the extra fermions, at the scale f, while the Higgs and the standard model gate bosons have masses which are regulated by the electroweak scale v. What about fermions? Which is the way to make fermion massive? For this one, use the partial compositeness paradigm and insert linear couplings between the standard model quarks and the operator and the extra fermion one. This is sketched in this Feynman diagram. You see this delta are the linear mixing. And in this way, the top mass is generated and also the top Yukawa coupling, and it is proportional to this linear interactions. It is clear from these few words that in this way, with the partial compositeness, we link the property of the Higgs of being composite to the property of the top to be partially composite. In other words, we sort of solve the problem that the top quark is the heaviest particle of the Standard Model. Its coupling to the Higgs is the largest of any particle, and there is no justification within the Standard Model for this property. So a possible explanation is exactly to link the dynamic which makes the Higgs boson a composite pseudo-Boson boson to the fact that the top is coupled to the Higgs via this mechanism, which is the partial compositeness. In other words, also the top is partially composite. And what about the Higgs mass? As I told you, it is generated by loops. An effective potential like Coleman-Weinberg can be calculated in these models. And this is because the Standard Model gauge couplings and also these linear couplings break explicitly the global G symmetry. Potential triggers the electroweak symmetry breaking, and for example, the electroweak scale can be derived from the explicit expression for the mass of the W, and this is the relation between the electroweak scale, the composite scale, and the vacuum expectation value of the Higgs. We also can derive a parametrical expression for the mass of the Higgs, which can be related to the mass of the lightest extra fermion described by the theory. Of course, these new particles have bounced from direct searches at the LHC. In fact, there is no indication of any new particle till now. And the present bound on this extra fermion is in the TeV region, so we are still in the ballpark with the LHC bounds, and we hope for some signals in the near future. Of course, a new physics model has to be tested against the experiment. As I just told you, one of the ingredients of the schemes is the formation of composite fermions, which are the partners of the quarks, of the Standard Model quarks. But also another important consequence is the fact that our Higgs is not a true Standard Model like Higgs. There are two properties which are important to disentangle this composite Higgs from the Standard Model Higgs. The first one is that it has nonlinear couplings due to the fact that the dynamics is the one of the boson bosons. And also in the expansion, this gives modification to the couplings. For example, the couplings to the vector bosons, to W and Z, and also to fermions. So precise measurements of the couplings of the Higgs to fermions and Ws can give indication and give bounds on the parameters of the model. This is, for example, a plot in which this is from Atlas, run 2, the experimental AC, and this is the correlation between these two kappa, kappa V and kappa F. Kappa V and this kappa are the so-called coupling modifiers. Is at the ratio between the coupling of the Higgs to V, that means gauge bosons, with respect to the Standard Model value. By combining several measurements, you see in this plot that the best fit, which is this cross, this black cross, is compatible within the errors with the Standard Model prediction. This is because LHC is a Hadron Collider, is not a precision machine, and in fact the Higgs couplings are still constrained within 10%, maybe 5% level. And this is not a big, don't give big bounds on our model. In particular, it's at a bound on F, the compositeness scales larger than 800 GeV, which is not so much. The high luminosity phase of the Large Hadron Collider, which will start within a few years and will end in 2040, will improve the sensitivity of a factor 5, not very much. So at the end of this stage, we will not be able to rule out these models just on the basis of the Higgs coupling measurements. The story could be different at I plus I minus collider, the future colliders which are proposed for the as a future colliders for studying particle physics. For example, here I just showed the deviation for the coupling to ZZ and to bottom anti-bottom of the Higgs in our 4D composite Higgs model, compared with the relative precision expected at high luminosity LHC, ILC, which is the International Linear Collider, and FCC-EE, which is the Future Circular Collider. You see that the black points corresponds to different choices of the parameters of the composite Higgs models. And for example, if you consider the benchmark A, which is the not blue, cyan, the cyan one, it corresponds to a scale of 1.6 TeV, and it is not excluded by the high luminosity LHC phase, but it will be excluded with a 10 sigma significance by the future I plus I minus collider. So if one based only on the Higgs coupling measurements, one should wait for this future collider to completely exclude these models. By the way, if you want to hear more about future collider escape, please ask me, because I have some slides, but I leave these slides as backup if we have time and you want to know something about it. Just a few words on extended composite models, Higgs models. As I told you, the one that I show you is just the minimal construction with only one doublet. Meaning that means that we are describing the 4 components of the Higgs as pseudonumber Goldstone bosons, but there's any new player in the game. For larger coset, one is able to describe other extension of the Higgs sector. In particular, one can give a composite formulation of the famous 2 Higgs doublet model by considering a coset of SO6 sub SO4 cross SO2. And while if you want to consider one doublet plus one singlet, it's sufficient to upgrade the coset to SO6 sub SO5. The composite to Higgs doublet model description was done by our group, and the construction is follows the same steps of the minimal 4-dimensional composite Higgs model, with a few specific assumptions about the strong sector, the global symmetry, and the spontaneous symmetry Breaky pattern. In this case, one describes the 2 doublets of Higgs, and which is the bonus of a composite Higgs description. For example, as you know, in 2Higgs doublet model, you have two CP even states, small h and capital H, and I mix with an angle theta, which is a free parameter of the model. If you use a description in terms of a composite dynamics, the theta angle is predicted by the dynamics, and it is predicted to be small, of the order of psi is v square over f square for large f. And also other prediction can be extracted by this description. For example, the masses of the extra X's grows linearly with the composite scale, and you also can predict the splitting between the masses, for example, of the charged X and the CP odd X in terms of the parameter of the strong dynamics. So this is just to show you that in these scenarios you are much more predictive with respect to the elementary 2Higgs doublet model ones, in which the potential is constructed in terms of free parameters. I don't know how much time do I have. Anyway, Jose, please tell me if I have to stop or I have to rush. But I would like to just sketch this new part of our research, which is related to the composite dynamics in the early universe. What I show you is that new physics in the Higgs sector gives deviations in the Higgs couplings. It also can give thank you, Jose. It also can give an indication for dark matter candidates, but I did not touch these things in this part of my talk. What I want to show you is that we can connect the composite dynamics to the thermal history of the universe. And in fact, a composite Higgs can, a composite Higgs scenario with one more scalar can trigger a strong first order phase transition with electroweak baryogenesis, and also give rise to a gravitational wave spectrum. In this way, we find a very important synergy between collider and cosmology. In the first instant of the universe, it was extremely hot and dense, so we can think of it as a cosmological collider. And as we know, a way to test the very first moments of the early universe is given by the gravitational waves, which was produced by very strong phenomena as black hole merging, but also strong first order phase transitions. Among these cosmological transitions, the electroweak phase transition is very important because it is responsible for mass generation. So one can think about the electroweak symmetry, which was exact at very high temperature. And during when the temperature goes down, one has the formation of bubbles of constant Higgs field. This bubble evolve and collide, and finally it's possible to have during this bubble formation a trigger of the baryogenesis. We know that this is very difficult within the standard model because the phase transition is a crossover, it's not a first order phase transition, and so we cannot have the condition for baryogenesis. So one can explore again the possibility of new physics in the early universe, that means new fields or new dynamics. Okay, this is what I already told you with the first slide. This is the thermal history. For higher temperature, the electroweak symmetry is restored. Then there is a critical temperature with two minima, which are degenerate and separated by a barrier, and the two phases coexist. And the transition starts at the bubble nucleation temperature, which I call here Tn. What is important is that the phase transition is strong first order, because the interaction with the field inside the bubble at the bubble surface, which is CP violating, create an asymmetry, a baryon asymmetry, which is washed out by sphalerons if the transition is not strong. And so this is what we want to reproduce with new physics, the fact that we can have a strong transition, first order phase transition. This can be achieved by adding a scalar singlet. In fact, in the potential you have further couplings, which are the portic of this new scalar lambda eta and the portal interactions. And in this way, you can achieve a transition which is a two-step phase transition. Namely, you can undergo an intermediate phase in which the new scalar has a VEV, and only after the Higgs get a VEV. This is important because it's possible to create a barrier between the two minima, and this gives origin to a strong phase transition. My time is quite over. Jose Ramon is saying that in the chat. So I just want to show the phase diagram of this model. In this region, the rate of bubble formation does not balance the Hubble expansion, so this is not a good region. Here, the global minimum is at T equal to 0, but in this region here, we have the portal interaction coupling and the extrascalar portic coupling. It is possible to have a two-step phase transition. So a first order phase transition, which is very strong. And here reported are also the strength of the phase transition, which is a crucial parameter for the electroweak baryogenesis. Concerning the electroweak baryogenesis, why we should consider a composite Higgs model instead of an elementary one? Okay, this is because we have a bonus in composite Higgs models due to the nonlinear dynamics of the Goldstone bosons. It is possible to have a physical phase in the top mass, which can give the additional source of CP violation, which is necessary for the electroweak baryogenesis. So our numerical calculation shows that it's possible to reproduce the observed baryon asymmetry with values of this B over F in the order of magnitude of some number over TV. And in fact, this is the blue region is the one where we can also have a gravitational wave spectrum, which hopefully will be detectable in the future space-based interferometers. And this region is also compatible with the electroweak baryogenesis. So in this very simple model, it seems that we could achieve all the good ingredients which are necessary to explain also the asymmetry, the matter-antimatter asymmetries, and maybe we could have some signals from the universe. Okay, my time is over, so I have some slides about the last 2 months growing tensions of the standard model, namely the latest results by the flavor experiments it's difficult for me, LHCb, and the G-2 from the Muon G-2 collaboration. These are the news of the last 2 months, which give us growing tension with respect to the standard model. Jose, tell me if I can go on or I have to stop here, maybe if there are questions. Okay, he said that I can, there are only a few slides. These results are saying us that the indirect searches are really powerful, and it was already clear in the history of particle physics. Let us think about the charm or the CKM metrics, which were needed to explain the CP violation observed in chaos, and lastly the top mass limit, which was extracted indirectly by the B0 bar mixing. So the precision measurement go well beyond the collision energy, and in particular the flavor change in network currents are very sensitive to probes of new physics. In particular, this rare decay of B to S, L plus, L minus in the standard model cannot go via 3-level interactions, because but only with this loop effect. And if one has a result which is much more, which is larger with respect to the standard model prediction, of course, one must invoke new physics. For example, at 3-level, one can have a leptoquark mediating the B to S, L plus, L minus decay. Leptoquarks are new particles which are predicted in grand unified theories, or also in the 2 Higgs double model that I mentioned before. One can have a loop, extra contribution by loops with the extra X particles. For the rare Bay decays, one can just parameterize the process with a point-like interaction, as in the Fermi description of neutron decay, and expand the Hamiltonian in terms of local operators and Wilson coefficients. And for this process in the standard model, there are 2 operators which are at work, O9 and O10. And in this plane, you can see the standard model prediction for the Wilson coefficients C9 and C10, and the result, the experimental result for coming from 3 different processes, which have a prediction which is not compatible, not completely compatible with the standard model. Among the various observables, the cleanest one is the so-called RK. The RK is a ratio, or branch ratio, of the B meson in K mu plus mu minus and K E plus E minus. And this is very clean because within the standard model, RK is equal to 1 due to the lepton flavor universality. actually, the measurement by the last measurement is a 3.1 sigma distant from the standard model prediction. And that can be explained, for example, with an exchange of a new particle like a lepton quark. Sorry. Yeah, like a lepton quark, as in this diagram. Of course, the lepton flavor universality is very well is predicted by the standard model, and also the experiment are in agreement with that. So the scale of new physics explaining these discrepancies has to be very, very high, 40 TeV. But it's very important to connect this tension from flavor physics with another tension which was announced 1 month ago, which comes from the measurement of the muon G-2 at Fermilab, which confirm the deviation from the standard model from the previous experiment, but the deviation is even larger. It's 4.2 sigma deviation. Of course, the deviation is with respect to the standard model, so one has to take in consideration the calculation done within the standard model, which is very accurate, but there is a part of this calculation which is the hadronic part, meaning that here in these loops we are exchanging hadrons, quarks, which has the bigger uncertainty. And also, I have to mention that just before the experimental results, some lattice results were published, and the value that they are used, the result of this lattice calculation is a little bit closer to the experimental one, so this result seems to weaken the discrepancy. So we have to wait of a confirmation of these results, but if this discrepancy is due to new physics, also in this case one has to search as a model which can reproduce the experimental results. In this case, you can also have light new physics, like a new Z prime with a very small mass, or again, or also we can have minimal models with dark matter explanation. As you know, there are a lot of papers proposing a solution of these two tensions, and they were out all together just after the publication of the experimental results. And what could be very, very interesting is to find a beyond standard model scenario in which it's possible to explain both the experimental results. For example, here I just quote two of them. One is invoking two scalar leptoquarks, the other one is invoking a simplified dark matter models in the loop. But anyway, I think we have to wait for this 5 sigma before climbing new physics, and also we have to wait a refinement of the theoretical error of the standard model. Okay, I finish here, and these are my conclusions. So after the Higgs discovery, we saw an explosion of research directions in beyond standard model physics. One would expect, okay, the Higgs is here, so we are happy with the standard model, but the effect was the opposite. We really saw an explosion of research directions. This is because there are many open questions in standard model, and naturalness remains a fruitful guidelines. I just show you one of these directions, which is given by the Higgs as a composite particle. And this is, even, in my opinion, even more interesting if we also consider the contribution of composite dynamics to the thermal history of the universe. Thank you very much. Sorry for being maybe too long.
Thank you very much, Stefania. Thank you very much. As you know, there's a little bit of delay between our talk and that in YouTube, so we might probably have to wait a few seconds. I'm now collecting questions. Are there any questions? Please write them in the chat. And while we get the questions in the chat, I would make one myself, which is obvious. Obviously, you said you had some few slides on the future of accelerator physics, and since you are part of the Preliminary European Committee for Future Accelerators, your opinion or your feelings about these where is the future going? And one of the things that surprises me is that if you can see the most appealing discrepancies that you've shown, or promising discrepancies that you've shown in your transparencies at the very end, do not really come from the high energy frontier, but they mostly come from the precision frontier. So one of my questions, that probably you will address in your transparencies, is whether this has changed the point of view of the panels for designing, or the panels thinking about future accelerators, together with the fact that no new physics has been found in the first few years of LHC. So are we thinking about moving to there's some noise there, sorry, to precision physics?
No, I understand your question.
Excuse me, there is one.
Jose Victor has the microphone on.
Someone is there changing.
I don't know if you're close, you can mute.
Jose Victor is making lots of. I cannot remove. One moment. Jose Victor, can you turn off your microphone? Jose Victor, there is a lot of noise there.
No, maybe it's not.
José Víctor, hay muchísimo ruido que viene de tu...
José,
de tu... Alguien con acento argentino está haciendo mucho ruido. Eso es. Ahora, perfecto. Muchas gracias.
Okay, perfect.
So,
no,
sorry, Stefania.
Your question is really important, and also really timing. This is the reason why, as you know, the committee
Stefania,
is
just 1 second.
Yeah.
I also have a question from the chat from Jesus, because he's working mostly in astrophysics and cosmology, and he's pointing to us that there are now several tensions, and he's, for instance, the Hubble tension and other tensions around. The question is whether there are similar tensions in our field. You've shown 2 of them, and probably maybe you have to make these a little bit clearer: the G-2 and the B. So we have these two tensions. Maybe you can comment on that, but before or after the future colliders, as you prefer.
No,
so maybe better the future colliders, and then we address the question.
Okay. Then I will ask some clarification on the question. No, I want just to answer your question about future colliders, because of course it's a very difficult decision to take in which direction to go in the future, for several reasons. First of all, of course, is money, because all this machine costs a lot of money, and so it's difficult also to take is both a political decision, because one has to put all together the willing of different countries, and also a decision based on the expenses, because all these machines are very expensive. Anyway, one has to take a decision not in a very long time from now, because all of them need a preparation. The technology has to be involved in not only in the construction of the machine, but also the detectors and things like that. Anyway, just to answer your question in a very, very easy way, if you want, the precision machine is the one which is already approved. This is the high luminosity LHC, because in this, the Large Hadron Collider is in the CERN tunnel, and the energy will remain the same. Actually, it will be upgraded to 14 TeV, and now it is 13. But what they are planning is to run with a very, very large statistics of events. In this, this will help processes with small production cross-section, and also very low energy and unusual signatures, and the large statistics will be good for analysis optimization and better control regions. So of course, this kind of physics will be done in the near future, because this machine, the upgrade of the Large Hadron Collider, the high luminosity option, is already approved and will go on. Concerning the future accelerators, if you have a higher energy, of course, these accelerators become the discovery accelerators, because you can direct product a heavier object, and you can increase the production cross-sections for many processes. Of course, you don't have the main way where to look for. It is exactly what I tell you before. It is new physics can be everywhere. Also, the explanation for the two discrepancies that I showed before can be given both with a new physics which is at very, very low scale or very, very high scale. So it's it is not a paved way, okay? Concerning the high luminosity LHC plan, we are here. Let me put my glasses because I don't see. 2020, actually, we had the schedule was a little modified due to the COVID pandemic, and the shutdown is a little bit longer with respect to the one which was planned, and the round 3 will start next year, 2022 up to 24, and the high luminosity option will start in 2027 up to 2040. I'm quite scared when I read this time. Anyway, in all these times, of course, it will be possible to accumulate 3,000 investment burn of luminosity, and so to finalize the precision program that we are speaking about before. In the meanwhile, the community proposed a lot of new machines. Here you see the names are the International Linear Collider, the Chinese collider, CLIC, which is Compact Linear International Collider, and so on. This project are still on the table, and for example, the FCC that I quoted before, and which is now the one which has maybe the larger probability to be constructed, is the Future Circular Collider at CERN, and it is constructed in a tunnel which is 100 kilometers long. It's very huge. Look, here you have the ring for a Large Hadron Collider, and this is the ring, okay, for the Future Circular Collider. In this collider, you have two options. Maybe the first one is to have two fasci, come si dice, no? I plus, I minus beams, okay, which start at the z-pole, then at the, you see the various options in energy. So for an accurate study of the z physics, of the w physics, 2040 means Higgs factory, okay? So you produce a plenty of Higgs particles, and this is the final energy in which you can produce top-anti-top pairs. So a study of the top physics, a very detailed study of the top physics. In parallel, the Chinese community is proposing the same machine, so a 100-kilometer tunnel, but it is not clear if they will upgrade also to proton-proton, and this is in the project of the CERN, but maybe it is not in the project of the collider in China. These were circular collider. There are still projects for future linear accelerators, in particular the International Linear Collider. Maybe you remember this was on the table when I really was young. It was a lot of years ago. It was called I don't remember. Anyway, the name was changed, and still in Japan are planning to construct this machine with the center of mass energy at the. It is they think to construct first this machine as a Higgs factory and then upgrade to higher energy. And there are still this CLIC project, which is the Compact Linear Collider, again in the CERN region. Recently, we have another proposal, which is the Muon Collider, which could offer an enormous potential for exploration of particle physics frontiers. But the muon colliders are challenging to realize, and there are still some issues to be solved concerning the possibility to realize this collider. Anyway, the 2020 update of the European Strategy for Particle Physics recommended a feasibility study for the FCC, including its post-FCC Hadron Collider stage and FCC HH, and the conceptual design report is expected for 2026. Of course, having an Higgs factory for physics, for the physics of the Higgs, will mean to check not only the couplings of the Higgs that I mentioned, but much more importantly, the trilinear coupling of the Higgs, because this will be the final check of the self-interaction of the Higgs and so of the standard model nature of the Higgs itself. After the high luminosity LHC stage, we will be able to measure lambda, the triple Higgs coupling, with a precision which is not better than 50%. So if you want to just really to shed light on the Higgs potential, you need the Higgs factories. Of course, you can tell me that this is only a part, okay, of our knowledge, and that other kind of physics can be done with not with these new machines, and indirect effects, as the one that I show you, can be hints for new physics. But in my opinion, collider physics is really important for our knowledge of the fundamental constituents of the matter.
Okay, thank you very much. Well, I agree with you also that collider physics, at least, is very important. At least probably to get to study Higgs with precision. So this I think probably is the most feasible thing, to try to go at least to determine with precision all the couplings that we don't know yet, and probably are not going to be easy to measure, if at all, at LHC. So now we had a question also from Jesus, who's from astrophysics.
But I don't understand.
Yes, the question is whether we do have some in particle physics. We do have some tensions that are to our field similar to the tension that they have, for instance, in the Hubble constant in astrophysics.
I don't know. The answer is that I don't know.
Well, if I may, could you show again the transparencies about the G-2 and the B's, which are, to my knowledge,
This one.
The tensions that we have. Yeah, the discrepancy between theory and experiment. I think you had a plot before that one. Where is it? Yeah, that one. So those are the things that you call experimental anomalies. I think it's probably the closest to the ones you have it in Hubble constant. But maybe you can comment to that, Stefania. What's the meaning of these things for someone who is not particle physicist?
Okay. So, for example, take this one for the G-2. Okay, you see. Here you have the standard model point, which is the green one, and then you have this.
If I may, Stefania, given that there are also people who are not particle physicists in the audience, maybe you can explain briefly into what is the G? What is G?
What is G? Okay.
What is G-2? What are we talking about that? And what is R? You explain a little bit RK, but maybe they don't understand what's the thing. So maybe you can explain that to a very basic level.
Okay, the muon is a elementary particle with spin 1/2. Okay, and also the electron. And the spin, you can imagine the spin as something like an angular momentum. Okay, because you can intervene if you think if you can do better than me.
I completely agree.
Let's do together. Okay, so Dirac was the first who, on the basis of quantum mechanics, who predicted that a particle with spin, okay, can have a zero magnetic factor in virtue of this property, which is equal to 2. This is the prediction which comes from quantum mechanics, okay? Actually, quantum mechanics is not the end of the story, because when you are at high energy, you have to deal also with another phenomenon, which is the creation of virtual particles and also their annihilation. This is the reason why particle physics is you have to put together the theory of relativity and quantum mechanics, and the unified description is in terms of field theory. Within field theory, then you can also take into account the effect of creation of virtual particles. So you can see this, for example, in this plot. You see, this is the diagram with which you can you calculate this factor. Okay, this is a photon, and these are the two muons. The two muons interact with the photons, and this is the Feynman diagram for this interaction. But if the energy is high, the muon, before interacting with the photon, can generate a new photon, which is, for example, absorbed by the other leg, by the other muon. This phenomena, and also these ones, can give a correction to the values of G, which is equal to 2, according to the quantum mechanics. Okay, so G minus 2 is a way to can be calculated by taking into account all these effects of creation and annihilation of virtual particles. It's not easy, but it's like that. So clearly, from theoretical point of view, the calculation has to be done by taking into account all the possible particles that, for example, this photon, let me think about a photon, but this can also be a mediator of the weak force, can create, okay, here in this bubble. Of course, if the content of particles is not only due to the standard model ones, but you have an extra particle, this extra particle also can contribute to this number. So it may happen that the G minus 2 that you calculate within the standard model, so assuming that the standard model is the final theory, okay, is not the one that you are measuring, because you are not taking into account extra contribution to this G minus 2. This is the reason why this discrepancy can be a hint for new physics or new interaction. So, for example, here, just to show you, this is the standard model prediction of this number, G minus 2 of the muon, and this is the error due to the fact that we are not able to calculate, even if you have the theory, to calculate it with an infinite accuracy. And this is the experimental value for the G minus 2 with the error. You see that the two are not compatible, also taking into account the relative errors, with and the discrepancy is here given in terms of standard deviation. And the discrepancy now is of the order of 4.2 standard deviation. We have a rule in physics that in order to claim an evidence, okay, of a discrepancy, we have to wait a 5 sigma discrepancy. So we wait for further results from the experimental point of view, and also maybe a refinement of the theoretical error in order to have this 5 sigma discrepancy. At that point, of course, one has to think about new physics, about the extra contribution to this G minus 2, which are not accounted within the standard model theory.
Thank you, Stefania. Yeah, that was very well explained. So those are, at the moment, these two are the most well-known or pressing, let's say, the most pressing tensions in particle physics. The lepton universality, RK is a ratio between the count, let's say, the decay. You have the ratio there, right? Yeah. So it's between the decay of a count to 2 muons and the decay of a count to 2 electrons. And you see that one of the interesting things about these things is that the muons, which are like fat electrons, are involved in both anomalies. So it's very likely, if these things persist, that there is something fishy with the muons that we don't understand yet. The difference with what you're saying with the Hubble tension is that here, your tensions, basically, if I understand correctly, are due to measurements in two different realms of astrophysics, or distances, basically.
Mm-hmm.
Here, the difference is not just the difference between measurements, because what Stefania was showing is just the difference between theory and experiment. And the problem is that in the theory part, we have the contributions from strong interactions, and strong interactions are extremely complicated to calculate because they are non-perturbative. So you have to devise non-perturbative techniques, and then not all theoreticians are completely happy with how these values are obtained. So what Stefania is showing you are what is usually known as consensus values from the theory part. And not everybody is completely sure that the theory part is calculated so well. So she's showing you the, let's say, statistical uncertainties and some systematic uncertainties, but we are afraid, many people, we are afraid that it's very likely that there are larger systematic uncertainties and maybe are not that. But that's why I left Stefania continue showing this part, because she was actually talking about these tensions. So are there any other questions? I haven't seen any other questions. I think the discussion has been going on for quite a while now, and it's been very interesting. Many people are expressing thank you to Stefania on the chat. So I think it's good time for us to stop here. Let me thank all of you who've been here in the channel, and also
a pleasure to be with you,
and also to Stefania. Thank you very much for coming and giving us this summary of the situation and some of your work as well. So thank you, everybody, and see you soon, I hope, in another IPARCOS colloquium. Thank you. Bye-bye.
Bye. Thanks.
Stefania, I think Jesus is probably coming now, and
okay.
And,
I'm sorry it was wrong. It's not easy.
I mean, I also let you talk because I knew they were probably going to talk about the tensions and all these things, which is what people like most at the end. It was okay. We've had quite a few people at the beginning. It's Friday, as I told you, and the problem is
no,
Friday. At some point, some of them have been leaving, but
it's recorded. So
until half of the talk, there were quite a few people, right? Then later on, you became more technical, and then probably the people who were not in the field, some of them left, but we still have quite a few people because we have a delay on the YouTube. I'm seeing the YouTube channel, so there are still some people there. Antonio is saying goodbye. Doado, some other people, nuclear physicists. They've.
Maybe, but
and some people are clapping also.
How are you?
You know?
Hi, Jesus.
Me?
Jesus?
Okay.
Yeah, we can hear you, yes.
Thank you very much, Stefania.
Okay.
Jose Victor, thank you. We are closing the session.
Okay, we're closing the session.
Jose Ramon?
Yes.
Are you there?
Yeah, I'm here. Can you hear me? You can hear me?
Or I cannot hear you. But anyhow.
No, Stefania can hear me.
Yeah.
We can leave the session. Bye.
Okay, anyway. Ciao a tutti.
Stefania
Jesus.
Can hear me well. Can hear me well here.
Yeah.
And I can hear her.